Hi, I'm JP Vasseur, Cisco Fellow, Head of Engineering for Machine Learning at Cisco, and I am delighted to co-present today with Federico Lovison, who is Senior Tech Lead in the ML Department of DNA. So Fede, welcome, and I think we're gonna have a great session. So,
Thanks.
it's not a new topic. We shipped this product a few years ago, but we have a lot of good news and updates, and we are going to give you a full demo of a product at the same time. All right, so what I'd like to do is just to start with a very gentle introduction about machine learning, but don't worry, we're going to go to the demo fairly quickly. Still, what an amazing progress we have seen over the past 40 years when you think about it, right? AI, ML was invented some time ago. We've seen many progress on the algorithmic side, but also in terms of processing power, and even more importantly, on the type of data. And I think that at Cisco, we've been working very hard on ML AI and a number of use cases. And in a few minutes, I will show you the journey we've been through for the past decade. I believe that we have built a very unique expertise on the use of statistical models and machine learning models for the network. So, there are many learning strategies, and I would just mention a very few of them, like unsupervised learning. Basically, in this case, you're just showing some data not being labeled to some algorithm, and there are multiple things you can do, such as grouping together similar items. I would say it's called clustering. You can also find some anomalies sometimes using some machine learning algorithm and things like that. So there are many things you can do. You can reduce the size of a space from a large number of dimensions while preserving some variability of a data set, and you can do the variance of a data set, and you can do a lot of stuff like that. Now we start to see, I won't talk too much about self-supervised learning because it's really emerging, and we are also working on it. It's a very promising approach where basically you can, learn some structure from a large, rich data set, on top of which you can use some labeling techniques to learn very quickly. We even believe that sometimes the human brain may be using such a similar approach for learning. But of course, we have learned a lot from supervised learning. So in this case, what you do, you show a labeled data set. So it could be, for example, showing some multiple data that relates to specific events, such as a malware. You show multiple examples with a malware, multiple examples without the malware. And usually we take this example of this use case of detecting cats versus dog and this sort of thing. So in this case, you have a label, and that's why we call it supervised learning, because you provide a labeled data set. But we don't always have a labeled data set. And then you probably heard of reinforcement learning. So in this case, you have some algorithms that have multiple actions that they can perform, and they get some reward based on the action, and basically they keep improving over time the decisions they make based on the target they're trying to achieve and some rewards/penalties. And of course, in many cases, we are combining multiple approaches. You can see sometimes deep reinforcement learning. In some systems, we're using both some supervised and unsupervised learning. It's never one single algorithm that we use. It's a system that is using a collection of approaches. So there are a lot of research topics, and the goal of this meeting today, this presentation, is not to go through a deep review of ML AI. I have other videos where I'm covering these topics. But I just still wanted to talk a little bit about what we call explainable AI, when we want the model to explain how it managed to reach a given conclusion or given outcome. You don't want it to be a pure black box for some use cases. You want to understand what led to a given outcome. Active learning is something very, very important as well. Transfer learning, where you can basically reuse a model that has been trained for a given task, and you want to transfer the knowledge to do another task. And that's something that most algorithms don't do so well. is sometimes called catastrophic forgetting. It's when you train, for example, for a given task and you change a little bit the task and then you need to retrain again. What we would like to do is to have some algorithms that are capable of learning multiple tasks at the same time, which is exactly the magic algorithm the human brain is using, and we'd love to know more about it, but it's going to take some time. Multitask learning speaks by itself. Ethical AI, adversarial AI, for example, where you may be able to fool some algorithm by changing a little bit, adding some noise, and because of that, you would be surprised by the outcome. But it's just that the human eye, for example, when you recognize a picture, it's very hard to fool, the human eye, right? And with some image recognition algorithm, for example, you may do some attacks so that you have an unexpected outcome. Okay, so a lot of activities in this area. Usually in our field of networking, when you look at multiple classes of algorithm, you usually see that you have with and without labels. And when you don't have any what we call usually ground truth, right? So you're looking at some issues, but nobody's telling you that this is a real issue or this is a real attack. You don't have any label. That's usually where people start, and because you believe that you can learn some baseline and what is outside of the baseline is necessarily an issue. And so people tend to jump on this kind of unsupervised approach, but it turns out to be the hard one, as opposed to a clean data set, but usually you need to clean up anyway, where you do the training based on labeled data. So why is unsupervised learning much harder? Because at the first sight you think, oh, well, I will learn the baseline and I'm going to find some anomalies. But an anomaly is not always an issue. First of all, it could be a statistical outlier, but it can happen. It doesn't mean that there is an issue. And of course, at some point, you always come up with a sort of notion of distance. And the notion of distance is sometimes a little bit hard to tune. And of course, we do see some discrepancy between what a machine finds interesting, such as an outlier, and what a human finds interesting, which is, hey, this is a real problem that needs to be sorted out. And of course, machines don't have any common sense, right? We know that. And so that's something that a lot of researchers are trying to solve, right? How can you provide some common sense to some kind of machine? How can you, for example, the notion of intuitive physics that humans do really, really well, which is extremely hard to train for a machine. And I wanted to share with you that experiment that we've made years ago, Fede, right? We exposed multiple subject matter experts to multiple anomalies, and the anomalies were generated by the machine, and we're trying to see if these experts would agree on what was a good anomaly and what was a bad anomaly. And unfortunately, I must say that there are groups of people that tend to agree together on both the good and the bad anomalies, but you also have some discrepancies and people that don't agree with each other on what is a good versus a bad anomaly. So is it a problem? Well, for the algorithm, it is a bad news because it means that there's no ground truth and it could be a little bit subjective. And of course, this is the work we have been doing at Cisco to develop this tool. I won't talk too much about correlation versus causation. I'm sure you heard about this. This is a very interesting, important, and complicated topic. But the bottom line is, think about this. Correlation is not causation. If you really want to come up with an approach, a scientific approach to figure out what caused the problem, so in other words, have a causal model, there are some approaches to do that, but they are usually very, very complicated. So how are we root causing with Cisco AI Network Analytics? First of all, I must say that there's no one size fits all, but there are a collection of approaches that we have been using when we designed the product. And we designed the product with the help of our customers, with a massive amount of data. But the good news, and you see that we have a layer that is in charge of doing root causing, but all of that is done automatically for you. You don't need to even understand how it's done. And again, you see a demo where we are going to show you this kind of root cause analysis, because sometimes you want to detect the anomaly, you want to reduce the number of anomalies, you want to have higher qualitative anomalies, and you also want to know what was the root cause if you want to fix the problem, of course. So what is the bottom line? The bottom line is you need to understand what you can do and what you cannot do with machine learning AI. And I really insist, because I've been driving ML AI for now 10 years. And the main lesson is don't jump on ML AI technology because you think this is a super cool technology and you'd like to use it. You need to use it if indeed you are trying to solve a problem that could be better solved by using ML AI. And we've been over pragmatic at Cisco, and I do believe this is very important as an approach to scale. So usually I've got questions like this, right? Do we really need ML AI? Well, not always. If you are trying to handle a simple problem and you can come up with a threshold, and the threshold is just good enough, right? You're just monitoring a single KPI like a CPU. You know that when you exceed 90% of usage of a CPU, then you need to do something about it. But if you're trying to do forecasting, you're trying to do anomaly detection, these sort of things, you cannot usually come up with a single rule-based mechanism. You need to start combining them, and at some point you need to learn simply and let the machine do it for you. So before we jump and talk more about wireless, which is the topic of today, I just wanted to give you a very quick walkthrough our journey at Cisco since we started a decade ago. We started off with the IoT, and in this context, we wanted to do optimized routing, detect some DDoS attacks. So we did that in 2012 before starting something called self-learning networks. Some of you may remember that. The goal was to use machine learning models at the edge of a network on-premise so that we could detect some anomalies that could be due to some attacks, such as exfiltration of data. And I think that was a beautiful, highly scalable architecture using very advanced technologies, highly distributed network that turned out to be a really great technology success. And then in 2016, we started to work on the first cloud-based AI platform known as Cisco AI, I believe this is the name of the platform today. But basically, we are gathering some data, as you can see on this chart. I'll go back to this chart pretty quickly. Of course, we anonymize the data. We're running a massive data lake that has been in operation for quite some time with thousands of customers on it. And then we are layering multiple use cases, multiple technologies, a large data lake that we're using for a product like the one we're talking about today. So what you see is, if you see this green band here, that's what is being computed by the machine learning algorithm to tell you when you're outside of something normal using long-term training. But I'm not going to talk too much about this because this is the whole point of the demo that Fede is going to give us. We looked also at the use of ML to do classification of devices and how we can tune some approaches to help and improve the accuracy of classification for devices. And then, of course, then what we thought was, hey, what about spoofing attacks? So you have a device coming in, claims to be a camera, and you want to use NetFlow to train some models to say, well, the model tells you that it's not the behavior of a camera, so it must be a spoofing attack. And in 2019, we started an amazing project that has been announced a few weeks ago. That was early May 2022, about what is called predictive networks and the ability to use machine learning to predict issues in terms of experience for the user, and then to have some proactive action to avoid the issue in the first place. I think this is one of the most interesting, exciting technology in the use ML for networking, but that's not the topic for today, and we have multiple videos covering that. Okay, so let's talk now about wireless. Finally, we're getting to wireless. So this is really one of the big buckets that we have in this product, Cisco AI Network Analytics. And the limitations, and I kept that slide, which is a few years old, was at the beginning to say, let's take the example of throughput. And I believe that we have one of the use cases we show to you is also about the throughput. So what is a good throughput for a user? Well, can I come up with a static threshold and say, if on average, each user connected to a given AP doesn't have X kilobit per second, it should be bad? It depends. It depends on the environment, right? It depends on how noisy is the building, the SNR, the RSSI, the number of users, the type of applications. So you can't really set a static threshold. You need to learn what you should expect considering some environment. And this is exactly what we're using ML to do that. So in this case, I'm just sharing with you some examples. You see how the 24 average throughput varies over time for multiple networks. And you see that in this case, you can see that for this network number one, you have some access points that are always good, you have other ones that are always bad. You see that it tends to vary, and look at the patterns, they are all different. So what that means is that you cannot come up with a static threshold that you can tune for a given network, for a given AP. It would be way too cumbersome to do, and you would have to adjust all the time, so it wouldn't scale anyway. We looked also at other interesting KPIs, right? So for example, the evolution of the onboarding time. You know that when you onboard or when you basically roam, by the way, you may experiment different timings. So in this case, each line is a different network. And what you can see is that here this is in seconds, right? And look at that. Some networks, they are around, the percentage of onboarding failures. I'm sorry, my mouse is pointing to the left now. You see that you have the percentage of onboarding failures. For some networks, it's close to 5%. Other networks, it's 35%. How could you come up with a single one? And of course, it may vary between locations and things like that. If you look now at the onboard, the fraction of failures, and I'm sorry because you can see that the titles shifted, but you can see what I'm referring to, of course, here is that the onboarding time varies in this case between 500 milliseconds and up to 4 seconds. And again, it could be because of a network, it could be because of a provisioning engine doing AAA authentication and all those things. So you need to learn. That's really the bottom line. And here are many other use cases of interest. I talked about the onboarding time, excessive roaming failures, DHCP time failures, AAA, and so on and so forth, both from a connection experience and an application experience. And I really want to insist on the fact that whether it is with DNA at Cisco and other products, we're getting very, very close to the application. We want to look at the application and the layer stack holistically, because this is really what we care about, which is, of course, we love a network. Of course, we love a layer 3, but we want to understand the correlation with the user application experience. Okay, let's say a few words about the architecture real quick. As I said before, we have some telemetry, very rich telemetry, very diverse, which is very important as well. And then we anonymize the data. The data is being anonymized and sent to a SAS engine. And this is in the SAS engine that we collect this rich and diverse data set, on top of which we're running multiple algorithms for sometimes a single use case, sometimes for multiple use cases. And then we can, of course, apply some cross-domain. And in this example, we are raising some anomalies and provide some insight as well. So there are basically, if you will, 3 layers here. The first one is a computation of a model. So the goal of this model here is basically to say, tell me, compute with a very high granularity. I want you to compute what should be the normal onboarding time. What should be the percentage of failures when you roam? And that's what you expect the algorithm to do. Then you have a second layer in charge of root causing and say, and here is the reason why we had an issue. And we have the third one, which is about relevance learning, because as I said, Sometimes the feedback may be subjective. Maybe for some users, they may like more an anomaly of a given type as opposed to another one. And then you can provide this kind of feedback so that the engine will learn over time what you want to see, what you don't want to see, for example. So we basically have three big buckets that we will be covering during the demo. One is connectivity issues detection and analysis, where we talk sometimes about baselining, which is a bit, it can be a bit confusing because you can do some very naive baselining with some statistical models. You can use some machine learning to do that. This is what we do. And then you have another bucket, which is about trends. So you want to see over a longer period of time how the network evolves, whether you start to see that there is one access point in a cluster of access points that start to deviate a little bit from the other ones, in which case, globally, it's still, maybe, it could be still okay, but you want to see whether there is a trend. And we also have comparative analytics so that you can see how you stand with regards to similar networks. So the bottom line, and I keep talking about green band, right? We love a green band in this team, is basically this band that you see here, and where you monitor in real time what is basically the value of a given metric. And when you start to see that the value is going outside of the green band, then it does mean that there is an issue. And this is where we start to flag a red zone and say, here we have an issue, let's have a look and look at the root cause. Okay, so one key aspect with all kinds of anomaly detection and alarm system is really about the noise, right? This is a worst enemy because if you start raising too many of them, you don't pay attention to them. And so it's extremely important to raise a small number of relevant anomalies. And I'm just sharing with you a fairly old number here, but this is even better now. But in this case, you can see by how much we reduced the number of anomalies to a very small numbers. And I can tell you that when the system is raising the anomaly, you'd better have a look at it because it's very likely to be a real anomaly that still a human may have some hard time detect by himself or herself. Okay, so just a few words about telemetry and data lake. The network quality is a complex problem. I think that everybody agrees. And it is also interesting because you want to look at multiple aspects of telemetry. So in this case, you can look at ICE contextual information. You have a lot of data about the access point and the clients as well, with what I'm not sure this is still the name, is still the WSA telemetry, but this is coming from a controller where we can get a ton of information about what's going on. If you go now to the routers and the switches and you go in the WAN, you start to see other kind of telemetry, down to the data center. And of course, we have a lot of servers we're using like ICE and DHCP and things like that. So we collect all of this telemetry. And sometimes we may even need NetFlow. I mentioned the use case about detecting a strange behavior that would tell us about a spoofing attack. In this case, you need to understand what's going on. So you may want to look at NetFlow for that. There are some other aspects where it could be very useful also to look at NetFlow to understand some patterns at the layer 7. This is a very rich source of data. The one advice that I would have is, of course, to check the quality of the telemetry, because we usually sometimes say garbage in, garbage out. And so don't expect that the algorithm will do some triage of what is noise, what is bad quality. This is the opposite. In reality, some algorithms are very sensitive to noise, other algorithms are less sensitive to noise, but the ability to look at the telemetry quality is extremely important. And yes, you can have some incorrect telemetry for a number of reasons. It could be that it could be some bugs, of course. It could be that some telemetry is missing also. They are grouped in different ways. You can have some packet drops on the way. You may not, it may not be, black or white. So if you're using, for example, 20 different features or hundreds of features, some of them, they start to be missing. And you need to think about this so that you understand what will be the outcome of the algorithm. And you want to detect it as well. So all of that is not about beautiful plots, right? And I'd like to say a few words about this because we've been looking at the telemetry as a little bit of an afterthought, I would say, when you look at the telemetry just so that you can look at the monitoring of a network. But in reality, and I spent years and years at the IETF chairing some working groups, we made mandatory to have some security section in RFCs at the IETF. I was part of a, very early working groups mandating to have also manageability section on how to manage the protocol, but also how to have a rich telemetry to understand what's going on. What I do believe is fascinating is that now we're not looking at the telemetry to check the health of the network, but we're using this telemetry to make decisions about the network as well with automation and machine learning in this case. So when you start closing a loop, you are really using telemetry, not just to check, but to make the right decision. And in some cases, some KPI may be fairly easy to interpret. You may not need anything. If you look again at the CPU usage of the heat, the temperature, you have the single KPI, that's probably okay. But there are KPIs that are a bit more noisy, and you need to do some signaling processing on top so that you understand what's going on. And in some cases, they may be even harder to interpret. And this is really where machine learning may start to kick in. So one of our most precious assets at Cisco is, of course, the data lake. We have a vast number of customers. We have, not just a volume of data. So, I kept this slide because it's an old one. We're going to share with you in a few minutes the new numbers, but that was years ago when we had, I would say, only 168 million onboarding weekly. Can you believe it? Now I think we're hitting 2 billion with a B, 2 billion onboarding events a week. So that gives you an idea. And the volume of data is extremely important, but that's not sufficient. What you want also is data quality. I just talked about it. So you need to make sure that you have some processing. We're using some MLOps features in our platform so that we keep monitoring the telemetry. When we have missing telemetry, we fix the telemetry and stuff like that. And we also want to make sure that you have diversity as well, because it's not sufficient. If you keep feeding the algorithm with the same type of telemetry, it's great, but that's not going to help you. You need to have diversity in the type of telemetry. So in this case, I have a video that goes through all of this where I'm showing with some self-organizing maps, we can study how diverse the telemetry is and how it helps the algorithm. And of course, as part of the MLOps, we are also monitoring the quality of the anomalies that we are raising when you start to see some shifting of the accuracy of the prediction and all the things, right? It's a very rich platform that we put together over the years. So I was telling you, I'm just sharing some latest numbers. In this case, you see the number of unique access points that we have on the system, above 1,500,000. The number of unique clients that we see is more than 25 million and more than 2 billion wireless client onboarding events. So that just gives you an idea on how rich the data, how diverse the data is, and that's also why we can have so high performance. So I won't talk too much about this. I think that I said enough about machine learning and monitoring, what we call MLOps. Also, the fact that it's not a one-shot event, right? You need to have a platform in charge of that. And we start to see in the cloud world, obviously, more and more tooling, which is great, but we still have to inject some knowledge, expertise, and really understand the telemetry so that we can do what is appropriate for it. But without any further ado, now comes the time where we go live and we are showing you what this tool is about. And before I hand over to Fede, I want to say that we haven't done all of that because we thought that ML AI would be really cool and we had to jump on some new technologies. Of course not. We always start at Cisco with the use case and what we have to solve. And I think this is very important to mention that. And it's extremely satisfactory when after years of, because we shipped this product in 2019, and we started to think about it in 2015, 16, you start to see amazing results. And we're just going to show you what we mean by results. So Fede, now the floor is yours. And I will conclude with just a few slides to talk about the future.
Thank you, JP. Thank you for the introduction, because this helps us now to deep dive into what the actual results are. And as we mentioned, based on the architecture that we are demoing today, which is based on Cisco DNA Center, what I'm going to show you is exactly what a normal user would see when using the product with real data. This is actually real data from a real live network deployment. The only difference between what we will see today and what the actual customer behind the data we're showing today is the fact that the data I have on my own DNA Center cluster is anonymized, because we don't have the key to decrypt the sensitive fields, because everything that is sensitive, such as IP addresses, location names, MAC addresses, and all this type of data is encrypted for privacy reasons. Besides that, the results that you are going to see today are absolutely coming live from a live network. With that said, a user enabling Cisco AI Network Analytics on their Cisco DNA Center appliance, we will start seeing their data exported to the cloud. Data processing will happen in the cloud, but then the results will be then available again directly from the Cisco DNA Center user interface. So under the assurance menu, we will find different menu links to the different features. So for example, starting from issues, we describe baselining used for anomaly detection. This is where the cloud system will publish anomalies found using the machine learning driven baselining, along with the issues that are generated on premise on the DNA Center. So those workflows are fully integrated and unified. And then there are specific use cases that are exclusive to the use of this product, and they are split into different categories. We will see trends and insights for long-term trending and long-term performance analysis, network heat maps, providing an overview of the network performance across multiple KPIs. Peer comparisons is an interesting use case, allowing to compare what the network performance looks like on your local network versus other networks that are similar outside, so from other customers, even though everything is aggregated and anonymized for privacy reasons again, but this gives you a benchmark of where you stand with respect to a given KPI with respect to other networks. Network comparison takes a closer look into the understanding what is a low, medium, high performance across the local network. And again, we allow to expose different dimensions, allowing to identify areas of the network that might need some enhancements. But I would start from baselines. Baselines is a dashboard that we recently introduced where it allows to, first of all, get an overview of the network. So here I'm going to show you, as JP was mentioning before, right? One of the reasons why we use baselining is because even though you might have one large network, we expect the behavior to be different across different sites, across different KPIs. For example, here we want to show you an overview. All the bubbles that you see on this beastworm chart, they represent buildings in the network. And this will show you how they look like over the selected period of time. Here I picked the last 7 days with respect to onboarding time. So the position on the x-axis shows the typical onboarding time at those buildings. You will see that there are the majority, the big chunk of buildings, they are around 1 second, which is pretty good. But at the same time, we can identify some buildings that show up as outliers where the typical onboarding time is higher, around more than 3 seconds in this case. But then when you want to look at buildings, one thing is looking at the actual network performance. The other thing is understanding the client impact, because of course we care about all our buildings, but where we have more clients, we expect impact to be larger. This is why the size of these circles represent the actual typical number of clients observed on a daily basis over these sites over the selected period of time. The larger it is, the busier it is. And eventually, we also encode using colors whether or not the AI-driven baselining identified issues. So whether there were anomalies detected on those sites. Now, if I pick one building of this, because I pick this one because this is visually the largest building I have. It's along the groups of buildings that typically seem to have a good behavior. We see it in the left-hand side of the chart, but there were issues. We got three issues. So now if I click on this, we will jump into the building view where we can deep dive and visualize all the different KPIs where we have a baseline for this specific building. We also have multiple SSIDs, so we can kind of start observing what is the typical behavior for this building over a specific period of time with respect to multiple KPIs. And here we have onboarding time, onboarding failures, we have DHCP time, authentication time, also association failures. So here you can see, as you saw in the slides before, this visualization of a green band, which is the what the machine learning model predicted to be the normal range. And this is important to mention that this green band, as you can see, varies as the network conditions change. And even for the same KPI in the same building, you see how different SSIDs have completely different performance, both the actual performance, which is the one visualized in the blue line, as well as the expected one. So the baseline really represents how not all sites are the same, how not all SSIDs are the same, and the baselines learns what the normal behavior is, using that as a reference to raise anomalies. So here you can see, for example, how the KPIs varied over time, and issues. So when we have anomalies, are highlighted in with those red bands, highlighting that at that time there was an anomaly that is considered to be an issue, and allowing them to click, so to open and deep dive into the actual issue. So here we see a zoom in into this specific time frame. Here again, we are looking into a specific SSID at one specific building, at one specific time range. Here we can see that we were expecting at this time the onboarding failures to be below 10%, but we got 20%, almost 20% of failure rates. This is considered to be an issue. This is considered to be an anomaly. But why did this happen? So here is where the root cause analysis features we have come into play to help you understanding what happened at that time. So we can see that the majority of failures that we observed were around AAA. So authentication was failing a lot for clients during this time. Many clients ended up being blacklisted, so failing to connect to the network. This baseline is determined at the, again, SSID and building side, but we can start digging into the individual access points having issues. So here we highlight, as part of the workflow, what have been the worst access points, trying to understand not only the authentication problems, but all the different issues that have been observed on the network, and how much of them happen on what access points. So to understand what have been the most affected APs. And this is, again, the goal is to go from a baseline, which is the building level, down to the individual floor and actual access point. So this is an example of an issue, how we got you to understand that, authentication was the culprit at this time. Also, this visualization allows that to see that at that site, at that same time, there was another SSID affected. And if we click on that, again, we see the actual baseline for the building. And by looking into the root cause analysis, once again, we see that authentication failures were the culprit. So definitely something to do with the AAA server to be verified next. With this said, besides what we can see when an issue occurred, this baseline dashboard aims at giving you visibility about how the network behavior evolves over time, because you can always compare what is the expectation based on the learning versus what the actual performance looked like. And here, for example, you can always go into more details for a specific combination of site and KPI, where we can understand better, not only when there is an issue, right? What we saw before, it was a detailed root cause analysis for an issue. Here we can analyze this irrespective of an issue. We can see what are the most, where most failures happen, what are the actual access points, what are the specific device types that are mostly affected. And yeah.
And we have to say, by the way, Fede, that all of that is fully automatic, because as I love what you showed, with the band, and you showed that for different SSID, for example, right, you have very different shape of bands, and it could be, the width and stuff like that. So they are all different because they learn automatically.
Absolutely. So and this is about the deployment, right? All you need to do to enable these features is manage the devices through DNA Center, so that DNA Center can provision the configurations to the devices. But then as the devices start sending telemetry, and you enable the cloud service to start the data processing out of the exported data in the cloud, from that point on, everything is automatic. And both the learning, everything is fully in self-driving mode. Now here, an example of what I was showing. When you go to the details, you can again see the baseline. You can see how many clients were connected. We can see the breakdown of failures by floor, by client types. And again, we can drill down to the individual access points. So we can see what are the most affected areas of the network. And again, this is accessible irrespective of whether there was an issue or not. So this can be used both for troubleshooting as well as for planning or enhancing the network and the client experience. Having said that, here we saw an example of onboarding failures issues, but I want to show you as well what a throughput issue looks like. So this is, as JP introduced before, right? We have several use cases around throughput. So in this case, you can see what the green band looks like. This is a prediction of the expected throughput for a specific radio with respect to a specific class of application, in this case, collaboration. So everything having to do with voice or video conferencing, for example. And even here, we can go down to the root cause analysis. For example, here it's showing that at this time, the throughput for collaboration apps was expected to be, for example, here, up to 20 meg per second, but it was very low. Actually, it was less than 10 kilobit per second. So something was definitely wrong there. And the root cause analysis automatically points out interesting KPIs that help to understand what happened on that specific radio at that time. So here you can see, for example, the network conditions were leading to lots of retransmissions over the air, which impacted the collaboration applications. So with this said, I would like to show you other use cases that are related to the long-term trending. So if we go back to the assurance menu, I want to show you trends and insights.
And while you do that, Fede, we can mention too that we worked very hard on the grouping of the application, because depending on what you're trying to achieve, you have multiple ways to group per class of application, and they all have very different dynamics. So that's something we did along the way when we designed the system, was to find the best grouping, looking at the classification of applications, and have a dedicated machine learning algorithm per class of applications. And we see now the next one showing up.
Yes, absolutely. So the use case I'm going to show you now, it's the latest we added to the large collection of use cases we started developing a few years ago. So this is something really new. It's being available since the early 2022. And what this is about is identifying access points that have been delivering poor client experience over a long period of time. So again, we focus on the client experience, and we don't, unlike the baseline we showed before, where yes, we learn what the behavior should be, what the expected behavior is at any given point in time. And we raise anomalies when there is an anomaly, a deviation on at a specific time. That's very important to identify issues when they happen sporadically, but there are areas of the network where they are constantly or providing suboptimal client experience. And this is what this feature is about. So in this case, we look at the long term. We look at 4 weeks, sliding window of 4 weeks. So every week we compute these insights again. And here we try to isolate among the most active access points on the networks, the ones that have been constantly providing poor client experience. And again, we do a multi-dimensional analysis to determine what the client experience is, considering many KPIs, including coverage, of course, but also retransmissions, packet failures, data rates. So we use many KPIs to determine what the client experience looks like. And then we use machine learning techniques to group those radios and compare them with the good radios in the network. So we automatically create two groups of radios inside the customer network, and we use them to even automatically determine the root cause. When we see the bad radios offering poor client experience, what do they do different with respect to the good ones? And the result is that the algorithm automatically extracts a weighted list of KPIs. So here we're not looking at KPIs in isolation. This is truly a long-term, multidimensional data analysis. And we cover several potential root causes that go from deployment, capacity, configuration issues that can explain a specific behavior. So, and this is presented to the user in a summary view like you are seeing on the screen right now, with a series of cards that explain what radios and how many of them, for a given band as well, they have been affected by a potential root cause during the past 4 weeks of time. And we can gauge even the impact by the number of clients that were connecting and suffering for poor client experience during this time. So we explain why we believe that those 14 radios, they have been quite busy looking at the number of endpoints, but most likely the AP density here is low because, again, we see clients are suffering. The client experience is not good. But how can we explain this? So here we say, look, we saw that those radios have been having many clients, so lots of large impact. For a long period of time, the client experience was bad. And we also noticed that if we compare these radios with the other radios in the network that didn't have client experience issues, you see that these radios typically have the transmission power is higher than the other ones. This typically indicates, so the transmission power per se is not a bad thing, but when it comes as when we see it aligned with the bad client experience, we see, oh, look, this is a difference with the good radios in the network. If these radios need to keep their power higher and your clients are suffering, most likely we need to improve the density of access points in this area. That's why we say this is about low AP density. Now, again, here we are looking into a group of radios. Now we said we have 14 radios. Now we want to deep dive and understand each of them, what they are, where they are, and what is going on with those radios. So this is where we present this table. We determine the impact of this type of issue in this specific radio. The impact per se is a function of the different KPIs that we use to determine the client experience, the number of affected clients, and for those KPIs, not only the number of KPIs, but even how bad they were with respect to the good access points. And you can click on these APs to reach into a detailed view. So now we are really deep diving into the single access point. So we have the access point name. We know that this happened at 5 gigahertz. We know the location where it happened. There is an integration with the AP360 flow from DNA Assurance. So DNA Assurance locally can provide additional information about other issues detected by the system during this specific time frame for these access points. But now let me show you, okay, why do we believe that this radio was delivering poor client experience? So look at this. Coverage seems to be way better, way worse actually, because we see how the RSSI and SNR distributions are very different from the good radios, the reference radios that we see depicted in blue. And on top of that, we see that this also has an impact on the actual data rates being used by the clients. Typically, other radios in the network, they use very often data rates which are above 100 megs, while this problematic radio often falls down to very low data rates. And this is how we determine that, yeah, for sure, the client experience on this radio is not great. And why? What do we explain? And here we see the low AP density because this radio always had this high power with respect to the other radios. We can see that there are different potential root causes we can identify with this method. So for example, here we can see another example where completely different KPIs. And again, I want to stress the fact that this is fully automated and we don't look into a single KPI. In this case, we see the root cause is composed by two different KPIs. For example, the co-channel interference and the channel utilization has been way higher on these radios with respect to the reference ones. And once again, if I click on a radio to see the details, we can see even how the both the explanation for the client experience is very different. In this case, we're not talking about coverage. Here we see there are lots of packet retries, lots of packet failures. And when it comes to the root cause, yes, we see channel utilization is very high. This is most likely caused by co-channel interference. So this will probably require not redeployment of access points, but reconfiguration of RF profiles to improve the channel utilization in this area. We can also see that the AP model for this problematic radio we are looking at is different from the reference access point. So this is a 3702 AP in quite, well, relatively old AP model, where we see that among the reference radios, the majority are newer generation of access points. So this is also an indication sometimes that, okay, different models of access points are performing differently. So, and so this is really aimed at pinpointing those APs. But again, we start from the client experience and we explain it by doing this multidimensional analysis. With this said, among the trends and insights on top of the feature I just displayed, which is about client experience, we have this feature called trends, where we want to identify outliers. We want to identify deviations when the behavior of the network is changing over time. And once again, we have different granularities. We can look into weekly deviations, daily deviations for a number of KPIs, considering capacity, throughput as an example here. So what does this look like? So here we want to show and give an overview about, here we're looking to a specific site. So we see a specific location and we see what the access points at this site looked like over several days in a week with respect to client count. And here the algorithm pinpoints that this specific radio has observed a significant deviation, so a deviation which has been higher than the rest of the peer access points at the same site with respect to client count. So for example, we went from a maximum of 50 clients to just 5 clients a couple of days later. So even this one even though this is not an issue per se, this is a way to identify when things start changing over the network or to identify how the network performance varies over different periods of time.
And I think this is a great example, Fede, because in this case, you guys can see that if you were to use some threshold and you would apply the same threshold to all APs, still, as you said, Fede, it wouldn't be an issue. But the fact that it is deviating shows that there must be something a little bit suspicious. And what you have seen with the different examples where you see grouping for, so we use multiple kind of distances. We use Kolmogorov distances here, for example, and you start looking at the APs. The example you gave about the APs was fantastic because you see that the distribution of interferences between the well-performing, ill-performing APs, you can, this way you can root cause, you can do a lot of very interesting things and good outcome thanks to ML.
Yes. Okay. And well, just to move on, because I don't want to, I really want to show you all the features we have because we range across. So we saw the baselining and issues, we saw the long-term trending and long-term performance analysis. And now I want to show you something about the comparative analytics features we offer. So starting from peer comparison, which is quite unique and enabled by the fact that all the computation happens in the cloud. So we have the ability of do clustering across network telemetry for multiple customers belonging to different verticals or looking into the characteristics of the actual network based on a number of parameters. We group together networks that are similar by size, by type of devices, etc., etc. And now we use these aggregated data set coming from multiple external customers and compare it with the local network. So you can have a benchmark of how your network is performing with respect of other similar networks. So as you can see here, by default, you can see KPIs that there are several KPIs that you can do this comparison on. You can see, for example, here for RSSI, the RSSI in 2.4 seems to be lower in our network than what our peers tend to say. Whereas, for example, in 5 gigahertz, the coverage and the RSSI and measurement that we see in 5 gigahertz, this seems to be more aligned with what our industry peers look like. But then even these features have been evolving over time, so we have been adding new KPIs. So if we started with RF-related issues, we recently added new KPIs that also cover the different aspects. For example, comparing what are the typical onboarding failures on your network versus your peers. So what are the most likely reasons for clients to fail to onboard? And here you can really do a comparison. What you observe on your network versus what happens out there. And here you can see that there are differences. There are some KPIs are similar, but some other error codes are different. For example, here we see in our network, we see the topmost reason for client failures in 5 gigahertz is client authentication, invalid authentication, whereas we see that typically in other networks, blacklisting seems to happen more often. This is just an example. We have the same even for roaming failures, where we can see, for example, in our network, we often observe max stations, so access points being oversubscribed, versus, for example, this issue is only happening, it's happening way less on other networks. This can be an indication of the fact that, again, as we saw from other use cases, in some areas of the network density might need to be added in order to accommodate additional network traffic. And with this, I also want to show you what we have for network comparison. So this is a comparison happening within the network. So we can compare both how buildings are performing or different families of IP models or endpoints. So for example, the way this works, we always process 1 week of data and we create 3 buckets automatically using, again, clustering techniques using machine learning to try to determine week over week, well, day after day on a sliding window to say, what has been the low, medium, high? How can we group together and determine 3 buckets for low, medium, high for a number of KPIs across the entire network? And then we can allow you to pick 2 categories of, for example, comparing 2 buildings or comparing different IP models, just as an example. And again, with by band from different KPIs. And here we can show, for example, how often an IP of one category falls into a low, medium, high bucket across the different categories. And this can help to understand improvements that can be applied to the network. For example, if you see that some buildings tend to be on the low side for throughput, for example, more than another building, or if a given class of IP models also tend to have more packet retransmissions than other AP types, or even we can take this comparison at the endpoint level. So we can see, for example, well, what is the AAA time for, let me select, for example, if I want to see, I know that there is a good sample of Windows machines connecting to this network, and I want to compare them with, I don't know, I want to say, let's say Android devices. So for example, AAA, what devices seem to be faster with AAA? Here we see that Windows in Windows workstation, they tend to be slow less than 1% of the time, which is good. But the 8% of the time they are in this medium bucket, which means it might take up to 6 seconds to authenticate. Whereas, okay, 90% of the times they tend to authenticate faster within 1.5 seconds. And but if you see, for example, Android devices, they seem to be, well, 99% or almost all the times in the fast bucket. In this case, you can also get some insights about what devices types tend to perform better or worse in the network over a specific period of time. And these slow, medium, high, or low, medium, high buckets are dynamically computed every day based on what is observed in the network. So even here, no static thresholds, and a fully automated, fully dynamic algorithms used to classify, let's say, the performance on the network.
Super. Super. So I think that this concludes the demo, Fede.
This concludes the demo, and yes,
That's it. Thank you so much, because that's what I call a rich demo, right? It's not a demo you do in 30 seconds and you show a little screen and that's it. You know, we had a lot to show you.
There is a lot to show, exactly. And the list of use cases is growing constantly, which is something I'm really proud to share, because there is a lot of work to expand both the quality, so improve the quality of the existing use cases. And something you mentioned is about the fact of the thumb up, thumb down. Every single feature has the ability for the user to provide feedback about the quality of the issues, insights that we determine, and we use this information to constantly improve the quality. So this is one aspect of the constant evolution of the product, as well as the new use cases, as I will show you the fact of those new angles that we try to extract as much as value out of the rich telemetry we receive.
Absolutely. And you know, this thing about learning feedback could be using reinforcement learning, as I said, because you want to keep improving over time. So this leads me to the conclusion, and we really want to thank you for your attention. As Fede pointed out, we keep adding new models, we keep adding new KPIs. We looked at multivariate aspects. Is not in isolation, as you could see. We are constantly working on application behavioral analytics and how it correlates with the network, which is super important. We're going cross domains and things like that. So the next, I believe, one of the next big milestones for our industry that we've been talking about for some time as an industry is about self-healing networks and the ability to close the loop and take some action automatically. We are also heavily working, as I said at the beginning, very quickly on predictive networks. And for that one, there will be some other videos. But again, thank you for joining me today, Fede. I think that was fun to do together. That's something we wanted to do for some time, because again, we shipped the first release of this product in 2019, so about 2 years, a bit more than 2 years ago. But thank you for your attention. Stay tuned. We have a lot of new technologies to show you and how we can use machine learning in this context. Thank you. Thank you, Fede.
Thank you. Bye.
Bye.